really vaguely written out there, so we could pretty much go anywhere. If we're looking at your initial statement of how do I cheat on this, the cheat was that we stretched that double bond. Actually, no, we don't stretch the double bond with the Wittig. You take your double bond, but now you erase the oxygen and you replace it with your carbon. Oops, come on, pen, work with me. With your carbon, and you draw on whatever your R group is. And then you ditch the phosphorus. Okay. From that carbon, how many R groups could we potentially have? One more, because we're satisfying octets. So you could have another R there, so we could have an R1 and an R. If we're going to get extra specific, we should recognize that on the ketone side of it, we equally have R groups. So we could have an R2 and an R3. Right? So I'm trying to think of where I would have suggested a cheat. I don't remember the cheat that I was suggesting for this. Because the stretching the double bond doesn't quite make sense in this case. But what we're doing is erasing the oxygen and dropping that carbon in to replace it.
This is kind of like where I wrote the notes and where the cheat was.
Okay. So within that, and I understand where that's going, is that if we look at what I've got drawn in purple here, that's officially our Yilid, our Wittig reagent. Okay. If we're going to look at a true retrosynthesis, that's charged. We had to make that. So where did that come from? Okay. And so this is what you guys did 2 weeks ago, I think. We talked about how you would get to that reagent. And that reagent ultimately came from an alkyl halide. Right? You ran the alkyl halide with triphenylphosphine, did the substitution reaction to get the triphenylphosphine on there, and then you add a really strong base to deprotonate, to remove the hydrogen on that, so that you would get the strong nucleophile that could go through and do the attack and draw out the results that you wanted. Okay, so depending on where you're kind of being asked to go to in a retrosynthesis type system, you may be asked to go all the way back to the alkyl halide. You may be asked just to go back to the Yilid structure. So it's just going to kind of depend on what you're trying to process. Kind of makes sense so far? Okay. If we're going to switch gears kind of to a retrosynthesis, okay, we're being asked to make this compound. So I want to make that structure. So if we're looking at the core functionality within the Wittig, that core functionality is really just the double bond. I think I can get away with that. Looks a little weird to me. Okay, it's really just that functionality. So if I'm going through and now looking at my retrosynthesis, that double bond is where all the chemistry is happening. Okay, and if we look at this, we could say, okay, well, there's the double bond. One side of that double bond had R3, R2, and our oxygen, our carbonyl. So we go back up to there. Which side? So I'm going to have to break one of those pieces off, be it the blue piece or the red piece, to draw on my carbonyl. Which side should I do? Okay. So one option is we break it off there, and then we would say the alkyl halide is now the remaining piece. We can draw on our bromine. Everybody see what we did? Was that the only way to do it? No. Officially, I could have gone through and broken it where I put the alkyl halide here and the carbonyl there. Okay? And that's coming back to kind of the core chemistry that's happening within the Wittig. So we get two possible ways that we could go through and run this synthesis. Okay? How would we decide which one was better? would argue there's two processes. One is arguably more correct. Okay, so one option is understanding what's happening within these chemical reactions. When we're talking about the Wittig, actually the Wittig-Yilid reagent reacting with the carbonyl, you're doing a pi system interactions. For the most part, we don't really care about steric hindrance or anything like that. But to get to the Yilid reagent, you had to take that alkyl halide and run a sequence of reactions. Right? The first thing we had to do was react it with triphenylphosphine. Then what did we have to do? We needed our strong base, our butyl lithium, to go through and remove that hydrogen so that we had our strong nucleophile that could go through and run this reaction. Okay, so what Lorraine is referencing is that when we look at those steps of the Wittig, do those steps have some concerns that we might want to pay attention to? So for instance, that first step with triphenylphosphine, that first step, what kind of chemical reaction is that? Okay, that's a substitution as the chemical reaction. Officially, I actually meant to ask the mechanism, so good follow-up on that. This does run under an SN2 reaction. Okay, and if it's going to run under SN2, we want a sterically unhindered nucleophile. We don't get to choose our nucleophile, so that's kind of out of the way. The only thing we'd get to choose would be the substrate or our electrophile. What substrate or electrophile would be best for an SN2 mechanism? Primary. Okay? Primary is the least sterically hindered. That would be the best alkyl halide. So we could go up to our two suggested syntheses, look at the alkyl halide, and say which one of those is primary. Neither of them are. Okay? So just based off of looking at the first step that we would have to run, we're not seeing a clear differentiation between those. What about the second step? What's happening in the second step? Okay. This is really just going to be an acid-base reaction. Okay. It's the transfer of the hydrogen to our butyl lithium, depending on how you wanted to define that. And I left off some charges officially, or positives down there. Okay. We're really just looking at acid-base. You could try and call it an elimination. Acid-base is more appropriate. You've got a wicked strong base. You've got that hydrogen. We want to remove that hydrogen specifically. There's really only one choice of hydrogen because it's got to have that resonance option. So there aren't a whole lot of limitations there either. A less sterically hindered system would make that better. Okay? But we already established there was no difference between those. Okay? So do we have anything in our context to be able to say which one of these mechanisms is better than the other based off of the theory of how these reactions work? No. So how would we know which one was better? You would actually try it. You actually have to go into the lab and you would try them and be, oh, this one works better than that one. Okay? Which is an unfortunate answer for a lecture class because you're like, well, what if this shows up on a test? Okay? Well, in that particular scenario, you've got a couple things depending on where the question is being phrased. Okay? If it's being placed into the multiple choice, should you see both of these answers show up as possible answers? So really, yes, you should. Okay, which one's correct then? Okay, so should you see both of them show up as answers? Okay. Maybe if an extra answer choice was both of these. Okay? But if you don't see that both of these options, why are both of them showing up as answers? Someone screwed up. Okay? That's why they'd be both showing up. Someone screwed up. You don't have the context to know the difference between which of those should be better. That someone would be me. Okay? And I know that's hard for you in a test to be like, hey, is this screwed up? But this is where you have to rely on whoever's writing the test. Are they paying attention to the questions that are asked? Okay? in the first pass, writing the question, and then in the second pass, are they actually going through and looking at how students performed? Because if both of those answers showed up, you would see in the statistics at the end of the test wonky results. Those wonky results would make you go, hey, why is that question weird? If you were a proper person paying attention to it, okay, and you'd evaluate it and go, oh, dang, I screwed that up. That's why everybody's getting it wrong, because I didn't provide them the context to differentiate, or in this particular case, there wasn't a way to differentiate. Does that kind of make sense? Okay. I can tell you that I do try to minimize these mistakes on the test, and I do look at them after the fact. Not only do I look at them after the fact, I encourage you to look at them after the fact and be like, I don't know why I got this wrong. Because sometimes how the statistics fall, because it does come out as random, okay, I don't see it show up in the statistics, so I don't know to poke at it until someone comes up and says, hey, this doesn't make sense. And then I try to explain it and go, oh, crap, I really screwed that up. Does that make sense? Okay. Just kind of brutal honesty, every instructor should be doing the exact same thing. I cannot guarantee every instructor does that. I can only guarantee what I try to do. Okay. How else could this show up if not multiple choice? Show your work in the free response. Okay, so if I ask this in the free response, what would I expect to see as the answer? I would expect to see both of them as the answer. Okay? And maybe how the question was phrased, I would probably also put into that question, if there's more than one answer, explain to me why one is better than the other. Okay? Which is really vague, horrible language, but what it's trying to get you to do is to evaluate. So you can look at it and be like, well, they're the same. Okay, say they're the same. That's fine. Okay? What I'm trying to get at within those show your work is, what is your logic? Did you just memorize something, or are you actually thinking about the content? Make sense? And if you only drew one, that's easily half credit. Okay? And that's better than nothing. Does that help answer your question for what's going on with that? Could this be made more difficult? Yeah, always. It could always be made more difficult. And it can actually be made more difficult within the context of reactions that you already know. Because if we're talking about retrosynthesis, we're talking about how this product was potentially made. By showing the double bond, you know that's my site of reactivity, and I go, oh, I could do Wittig. Great, there's Wittig results. Do I have to show the double bond? So for instance, and we'll leave the double bond structure up there, what if you were asked for a retrosynthesis? It was this. Do you know how to interconvert between the double bond structure and that bottom one? So some people are saying, yes, this is what makes retrosynthesis challenging, is you would have to know the reagents that would allow you to do that. Well, what's different between the bottom structure I just drew and that initial retrosynthesis? Pi bond. True, that changed. What else changed? The number of hydrogens. Okay? So we could talk about reduction and oxidation behind these reactions. Okay? Depending on where that pi bond was placed, we could talk about different ways to navigate that. That becomes a more challenging question, because now you could say, well, where did I want that pi bond? Which hydrogens did I want removed? Okay? Because if we do that, we're no longer starting with that structure. You're being asked, how do I retrosynthesize this? And you say, well, I know I could reduce my alkene. Where do I want an alkene within this? So now it's, well, if I had an alkene, I could do a Wittig. Which would be the best Wittig? Well, the best Wittig is going to be the least substituted with my alkyl halide. So you could now select where that double bond was within the original structure. Because we've got effectively an infinite number, not infinite, but a lot of possibilities for where that double bond could go, you get lots of possible answers that could come out of that. Okay. Problem with lots of possible answers, sucks to grade. So typically when you're looking at retrosynthesis or synthesis reactions, they're chosen to very specifically narrow you in to one path because we don't want to grade 20 different possibilities. Kind of, sort of? Okay. Other questions? Okay, my turn. We roughly have 3 groups. Whoa. So, ABC, you got boards, roughly group off, it looks like we can pull off 3 to 4 per group. Okay, ABC, you guys get to choose. Once it's been selected, you can't choose it. Draw them up the board. What was the big change in all 3 cases? Yeah. This is somehow a methyl is being, without trying to use words that hold too much meaning, added to our structure. Okay, and added becomes a problem because that implies that we're doing an addition, and we aren't doing an addition necessarily in all of these cases. So if we're going through, there's a methyl change in each of these cases. Okay, we've got a methyl there, we've got a methyl here, and we have a methyl on that side. So let's go ahead and do the downward directions first, B, and address that one. Okay, so both groups did slightly different things. One group actually explicitly wrote things out, which I would argue is appropriate, okay, and is something that I was generally observing from everybody. I think a lot of people are holding content inside your head. When you're holding it correctly, it's fine. The problem is when it's incorrect, typically on an exam, that becomes problematic. So if you draw it out, that can help. That first draw out step that they did was acknowledge that you've got resonance, you've got the negative oxygen and the positive carbon. So if I'm going, wow, that didn't seem to fix much. If I'm going to look at going downwards towards B, I'm putting an extra carbon at that spot. Since I know the carbon is positive, or the blue carbon is positive, I know that new methyl group has to come in as a negative. Drawing a CH3 negative as a reagent, generally speaking, is bad. It should be neutralized. So the question is, what do you pair it up with? Okay. One of the natural reflexes that we're all going to fall into, unfortunately, is you go, oh, if I've got carbon, the easiest way to stabilize that is I just put a halogen next to it, and that simplifies my structure.
Or metal.
Okay. The problem with putting a halogen next to it is what charge is or what is the difference in electronegativity between the bromine and the carbon? Bromine is more electronegative, which means those electrons are going towards the bromine. The bromine carries the negative, and the carbon carries the positive. I wanted a negative carbon. Okay, so reflexing into immediately showing that is going to bite you a little bit if you don't at least double back and say, well, how would those electrons redistribute? Okay, so the carbon with bromine isn't going to work. It's not going to get me a negative carbon. Okay, so the group on our far right went through and said, okay, well, if I want a negative carbon, it needs to be connected to something that's less electronegative than it. Lithium. Lithium is by far less electronegative than that carbon, so the electrons should, whoops, as I draw the arrow wrong, should use an eraser, okay, should shift towards the carbon, giving us that negative carbon. That negative carbon could now potentially go through and react as a nucleophile, attack our positive carbon, and set us up within a following step. So step 1 and then step 2, H3O+. We would have to split that into 2 steps because the negative carbon would be so active that it would be quenched by the acid. So it has to split into 2 steps. Okay. I'm okay with that written out, though I do want to kind of point out here that this may not actually do what we want it to do. Okay, that lithium is so low in electronegativity that bond is so ionic, that carbon is so negative that instead of it acting as a nucleophile, it's going to act as a base. Okay, so again, I'm okay with this because you're showing the chemical flow, perfectly acceptable. Okay, but that particular ion is probably going to ruin the chemical reaction and it's going to do something other than what you want. Okay, so what else could we put there that was less electronegative, more electronegative than lithium, but still less electronegative than carbon? Okay. And since we have periodic tables, we could say almost anything, because we can see carbon on the far right, lithium on the far left. Any metal in that sequence should allow us to do this. Okay? It's just going to be a question of which one matches the context of what we've been talking about. Matching the context of what we've been talking about is the Grignard reagent, and we should be having magnesium in there. Magnesium being a +2 ion, we need another charge to balance that out. This is where you'd have your magnesium bromide. Okay? Kind of makes sense? So follow those charges, recognize those charges. Again, ideally write them out so that you can see them and think about them instead of holding it in your head. Make sense? Okay. If we look between A and C, okay, both groups went through and said, oh, I had to remove a hydrogen. I guess we'll color code, make C orange. We're removing a hydrogen out here, or we're removing a hydrogen out here, which means the first step of the reaction needs to be it needs to be an acid-base reaction. So I need to add a base. Okay. Deciding that process becomes kind of the tricky part, because if I go through and add a base for step 1 and a base for step 2, well, actually, sorry, let's just say base. What charge would my carbon become? My red carbon would then become our negative. I'm going to show it as partial negative because I still have the hydrogen connected to it. Okay, which then means to get the carbon, the new carbon, to react, what charge does that new carbon need to be? I need a positive carbon. So I would follow this in 2 steps. I'd have a base. I need a positive carbon. I can't show a positive carbon, particularly a zero-area positive carbon. So I need to stabilize that in some way. What atom could I connect to it? There's our bromine coming back. Okay, so, we did that wrong the last time, but we did it wrong the last time because what charge did we want the carbon to be? Negative. What charge do we want the carbon to be here? Positive. So this is perfectly acceptable. If we look at the routes that we've identified, we said for red, we need to add a base, CH3Br, fine. If we look at the orange, we add a base, CH3Br, fine. Except the methyl's going to a different spot. The methyl isn't driving that chemistry, it's the base. So now the question is, what base do you use to force that reaction to happen the way you want it to happen? Okay. So one option that was being suggested is something about acid strengths of those 2 spots. Those 2 spots have relatively similar acid-base characteristics. So looking at pKa, unfortunately, isn't going to help us out. You're looking at a very small difference in acidity between those. So what allows us to differentiate between those 2 paths?
Steric hindrance.
It's less steric hindrance, because steric hindrance, unfortunately, will chase us down the wrong path. Because if I go through and use steric hindrance, if I use T-butoxide, which path would I expect to get? I would expect to get orange, because steric hindrance would block the red hydrogen, and I would expect the orange path. Except when I use T-butoxide, what do I get? I get the red path.
So is this base strength? Or
Yes, it is about base strength, but I would prefer some different.
thermal?
There we go. Okay. So when we're looking at the differentiation between these two pathways, it comes down to kinetic versus thermodynamic. Okay. That orange route is the kinetic path. The red route is the thermodynamic path. As it's drawn, I would argue it's easier to see the kinetic path. Why is the orange one kinetic? It's more accessible. It's on the outside of the structure. So if we're looking at a base coming in to react, that's easy to react. Because it's easy to react, that's speed. That's kinetic. How can we tell thermodynamic?
Equilibrium stuff.
We look at the energy of the product and say, well, I've got a methyl group on a more substituted spot. Is that thermodynamically more stable? Does it make sense to put more carbons in the same space to be thermodynamically more stable? No. How the hell is that thermodynamic then? That's not the thermodynamic product. What's the thermodynamic product? And if you're like, well, it must be the orange one then. No! We said that was kinetic.
Intermediate.
The kinetic versus thermodynamic is coming in step 1. The products that we've got drawn out here are step 2. To determine our difference between kinetic and thermodynamic, we have to look at the product of step 1. The product of step 1 for the red route would be putting our negative charge here. In the orange route, it would be putting the negative charge over here. Can I tell kinetic versus thermodynamic yet? Well, we didn't do it earlier, so it must be good now. No, because I asked the question, of course. Why can I not use these structures to determine kinetic versus thermodynamic? It's not the best resonance structure. If we draw out the best resonance structure for these, what we're going to see is the enol form. Not zoomed in enough. For these. And if I now look at the best structure for each of these, what's the primary difference? We start with charge. The charge is the same in both, held on the same atom, so not relevant. What's the next most reactive thing within those structures? The pi bond. In the red case, that pi bond is more substituted than in the orange case. Because it is more substituted, that makes that enol thermodynamically more stable. Okay? So the red path is our thermodynamic path. So how would I decide which base to use? Well, I would look at my base and I would compare it to my best Lewis structure. My best Lewis structure is a negative oxygen versus negative oxygen. Those are equal stability, which is why when I use a negative oxygen as my base, I get the thermodynamic product. There's no differentiation between kinetic versus thermodynamic, or equal stability towards the thermodynamic. What happens if I switch to a different base? Well, what other base is there? NaH. And if we look at sodium hydride, we can delete the sodium right away. We're looking at a negative hydrogen. And we now compare negative hydrogen to negative oxygen. Which one's more stable? Negative oxygen by a long shot. Which means, which product do we get? The kinetic. Why? The base is irreversible. It immediately forms the kinetic, and it can't revert back to the starting material. If it could revert back to the starting material, then it has time to make the thermodynamic. But if I use a stupid strong base, all I get out of it is the kinetic. If I use just a strong base, we're still going to form the kinetic intermediate first, but with time and heat, that reverts backwards to making the thermodynamic structure 1, and then that propagates onwards to my final reaction because that product is now thermodynamically more stable and therefore irreversible. So when we talk about the terms reversible and irreversible, they're referring to different stages of our chemical reaction. We have to be kind of careful within those. So to differentiate these two paths, you can memorize. That's absolutely fair. Or you're looking at the nuances behind each of those pieces. Questions about that?
Did we say anything about heat and cold? When we say that first step?
So you could add temperatures to that if you really wanted to. Typically, it's not used in these cases because the base strength is so dramatically different. Okay. So could you use what we would refer to as a reversible base like T-butoxide, and then say you did it cold and fast? Well, if you did it cold and fast, what product are you going to get? You'll probably get the kinetic. But now we're messing with multiple variables. And while we can ask questions on that, that's now becoming a much more challenging question.
What if you just said base?
It's just, as soon as you change temperature, you're now again adding two different systems. So primarily it's focused just on the base strength. You can see temperature differences, but generally speaking, we're just looking at the base strength. I'll also add that typically when we look at the strong bases, we're almost always making it cold for stability reasons. Questions? That question look familiar to anybody? It is from the smart work. Smart work for next week. No one's looked at it yet. It's okay. But I figured I'd just look through it, see if there was anything interesting. Do y'all have other questions? Yeah. So it's officially kind of outside the scope of what you've got right now because you're looking at reagents that you're unfamiliar with. Okay, but are you familiar with any of those reagents? Grignard. Okay, so let's just go through and look at the Grignard. Okay, the question already said that there's a typo somewhere in this. That typo is unfortunately dramatic enough that you can make all sorts of changes to make the reaction work. Okay, so there's a lot of different ways that you could tackle and manipulate this question. So if we decided that CH3MGBr and H3O plus was the answer, how would we fix this so that it would be true? So first and foremost, what changed? So we can even delete that as an answer thing. What's the claim changed in this chemical reaction? Say again? Okay. We lost the pi bond. Okay, and you're saying we gained a hydrogen. It was added onto that oxygen, which I love as a statement. Which oxygen are you talking about? Are you talking about this low one or that high one? Okay, so let's go through. Is it this oxygen or is it this oxygen? I meant to color code that. I apologize. Blue or orange? Which one gained the hydrogen? right? And this becomes an interesting challenge. So if you're going to go through and say the blue, we're potentially missing something, okay? Elena, you went through and said the orange, so you challenged the majority of the class on this. Why? Okay? If we look at the backbone of this structure, we've got oxygen in two different locations, which means theoretically oxygen shows up in two different locations in the product too. We would have to make sure that when we translate that product across, that we're accounting for that backbone as appropriately as possible. And if we go through and account for that backbone as appropriately as possible, I've got 1, 2, 3, 4. The fifth carbon, it branches to give me 2 methyls. Okay? So if I count that out following the same number logic, 1, 2, 3, 4, fifth carbon, that doesn't branch out to 2 methyls. Oh, but I'm missing a methyl over here. What happened? This is 1, 2, 3, 4, 5. There's my 2 methyls. 1, 2, 3, 4, 5. What happened with the product? We flipped the molecule. Why? This is a fair, probably what's in your gut is a fair response. Why did we flip it? If that was your gut response, I feel a little better. No, it was an intentional flip. It was an intentional flip to say, are you paying attention to where your structure is in 3-dimensional space? Okay? Because you're responsible for that. And because you're responsible for that, if you don't like the way it's drawn, what should you do? Redraw it. Hopefully you redraw it better than I just did. There's my OH there. And we can call that, I guess the way I've got it labeled, the blue OH. So when we're looking at the changes in this chemical reaction, what was the change? Yes, I lost that pi bond initially, which is really hard to see. Which is really hard to see, so we'll erase that. I lost that pi bond and I gained a hydrogen at that spot. Make sense? Is that the only change? What was that? There's another hydrogen gained. Where's the other hydrogen gained? Position 2, there had to be another hydrogen. Back to my numbering. 1, 2, 3, 4, 5, 6. Does that make sense? So if we look at how the question is framed, the only thing that was changed is we added hydrogen. Do we have any reagents to add hydrogen? Yeah, what is our reagent? H3O doesn't add hydrogen. What does H3O add?
H3O.
H3O formally is not hydrogen. That's hydrogen ion. What does H3O plus add? It adds hydrogen and OH. H3O plus is a hydration reagent. It adds water. Here, all I want to add is hydrogen. So if we're going to use names, we could call it a hydrogenation. What reagent just adds hydrogen? Hydrochloric acid also adds chloride. H2. Okay? And if you're looking at the answer choices, remember, there's a typo, so let's not worry about the answer choices. Okay? What reagent would add H2? But we can't just add H2. So this is now, what do you guys remember back to our very first unit or the last unit in OChem 1? What was that, Helena?
What were the two, rainy or platinum?
Yeah. H2 and platinum. We have H2 and rainy nickel. We have H2 and it's usually palladium sulfate or something like that. And then I'm pretty sure I just drew that one wrong. Whatever. Sodium barite. I don't know. Or it would call it just straight up, this would be easier, poisoned. Okay. So those were our H2 addition reagents. When we talked about those addition reagents, those were addition reagents to what? Pi bonds? Because now we have two different pi bonds that we could talk about. We have our nonpolar pi bonds in unit 1, and this unit we have polar pi bonds. So when we first talked about these reagents, these were all nonpolar pi bonds. These last two are primarily for our nonpolar pi bonds. That H2 in platinum is an unfortunate one. I believe the textbook actually does a breakdown on it. That reagent can be used to reduce any pi bond. The problem becomes that you can change the pressure. Why would we change pressure? H2 is a gas. You can change pressure and temperature, and that targets specific pi bonds. I do not at all recommend memorizing the specific temperatures and pressures that are necessary to force different pi bond reductions. Okay? All I want you to know is that H2 in platinum is going to take out pi bonds. Okay? So if all I wanted to do was add H2, well, there you go. H2 in platinum. We use the reagent we already know. Yes, that works. But if we look at our answer choices, that was not one of our answer choices. Okay, so where we want to step back from is go back to what we discussed. How can I make an edit to the question? So how do I change the question so that answer choice B is correct? Okay, what are you going to change within the result? Okay, if we look at the changes in our results, we added hydrogens. Okay, so we'll try and color code this out a little bit better. We'll keep the standard things as purple. So if I wanted to do CH3MGBr, that's a Grignard reagent. Grignard's reagents react with polar pi bonds, so I want it to react with the carbon of our carbonyl position 2. So I would want to see a CH3 appear at carbon number 2. Step 2 would give me the OH, and ta-da, now I've got it fixed. Does that make sense? Okay. Is this going to work? No, why not? Because I asked the question. Do better. Not too many carbons. Say again? That alcohol has an acidic hydrogen on it. So when I add the Grignard, what's the Grignard do? It's going to take that hydrogen off. When it takes that hydrogen off, I no longer have the Grignard. It can't do the nucleophile attack. Okay? So this is a particular reagent. Doesn't work out great for us because we have that secondary functional group in there. This is largely why this question belongs in next week's content, because next week's content now says you've learned lots of single reactions, and we've looked at a single structure changing into a product. But what if that structure has multiple functional groups? How do you navigate around those issues? Right? So if we look at this particular case, if I want this reaction to happen, the CH3 attacks that carbon number 2, what do I have to do to the alcohol? It would be more broad than what you want to convert it to. There's the answer. If I want to react the carbonyl with a Grignard reagent, I have to protect that alcohol. That protecting is something that I would expect you to do next week's lectures. What I would expect of you is to look at a list of possible protecting groups and say, that's a good protecting group for alcohols, that's the one I'm going to use. I do not expect you to memorize any of those. Okay? So in this particular case, I just want you to be able to acknowledge where there's issues within this question. That's why I've left it there. But it is a massively flawed question. Does that make sense? As you learn more reagents, say that one, H plus and this dithiol followed by Raney nickel, you should figure out, well, what does that reagent do? Okay, how does it react? Once you know what it reacts with, you should then acknowledge what are some potential secondary things that could be complicated by that reagent. Well, for that reagent to work, what conditions must it run under? Acidic conditions. Do I have any basic functional groups within this? The carbonyl is not bad. Okay, and it turns out for this, and again, we're going to territory you don't know these reagents. That's actually the chemistry we want to leverage. We actually want to protonate the carbonyl so that the carbon of that carbonyl becomes more electrophilic. So that what can happen? My sulfur can react. Okay, so awesome sightline on the carbonyl being basic. Is there anything else that's basic? The alcohol. If I protonate the alcohol, it turns into a good leaving group. And if it turns into a good leaving group, what could my sulfur nucleophile do? It could attack there. Damn. So what I'm looking at is what that reagent is designed to do, and then say, are there other chemistries that could get in the way? So in this particular case, yeah, there are other chemistries getting in the way. I would want to, again, prevent the alcohol from reacting by throwing in a protecting group. Did not expect any of you to say the carbonyl was basic. So good on you. Because that is absolutely true.
Does the metal like clump the H2 together?
Say again?
Does the metal, does it clump it?
Raney nickel's mechanism, I don't know officially off the top of my head. It's a little bit complex. With the platinum ones, it's a little bit easier. The hydrogen sticks to the surface of the metal. So the metal helps to facilitate by bringing the two substrates together like an enzyme. What do we see in D? It's now basic conditions. Okay? Under basic conditions, what could potentially happen? We could look at acid-base reactions. So, do I have anything acidic in there? We do have the alcohol. Okay. Depending on how that reagent actually functions, is that acid-base reaction going to have an effect on the broader thing? You don't know what that reagent does, so don't panic yet. Okay? But that's the thought process that you should be rolling through. And if you haven't guessed, it is a complex process, which is why I screwed up and made a massive typo within the question. Because what I wanted to happen didn't happen because I missed all of these secondary things. If we look at that last reagent, have you seen that reagent before? That one gets a little bit weird with the mercury in it, but hopefully you would recognize the zinc and the HCl because that was our Lucas reagent. Zinc and HCl were used to convert alcohols into chlorides. Why is the mercury there? Because the mercury helps the zinc and the acid to react with the carbonyl. But it also reacts with alcohols. What else was in the structure? An alcohol. So that reagent adds a complexity because of that secondary functional group. Kind of makes sense? Okay. So what I'm asking you to go through and do within that footnote is how could you get these things to react? What things would you need to be aware of? Adding a protecting group changes a lot of this chemistry. So if it changes a lot of the chemistry, that's not an easy fix, An easier way to do it would be just delete the alcohol, right? If that alcohol is not there, that simplifies a lot of the chemistry. Now some of these things start to become active. But now we also run into the issue of, well, shoot. Rose, are you tapping? Yeah. It's okay. Let's just make it a little noise. We would have to change the reaction to figure out what those reagents did. Okay? So broader kind of statement, just to give you guys an idea, prelude to next week. All three of these reagents will add H2 to a polar pi bond. Okay. How they add, and actually it takes it a step further, it will add H2 to that polar pi bond in a way that you entirely lose the oxygen. So not just here we just put hydrogens on and we get an alcohol like we do with the Grignard. It full on loses the oxygen. So it's a full reduction. So they are pretty powerful reagents. But if you look at the conditions for each of those reagents, they vary acid and base strength. They vary nucleophile chemistry in each of those cases, which changes the conditions under the rest of our structure. So to decide why we would use one versus the other, we'd look at for those secondary functional groups and say, what are those secondary functional groups going to do? Would they get in the way or not? Kind of help? I've done this one like 10 times over. Let's try it this way. Andrew, what's the answer?
Probably A or B. Didn't I ask this one already?
We've done this one a whole bunch. Yeah. Actually, no. I changed my mind. We didn't do this one a whole bunch. What we did a whole bunch was with sodium hydroxide. Why is this one different than sodium hydroxide? Different base. What's the base in this one?
OAC.
That was outside.
Sorry,
Yeah.
it's automatic.
This is AC. So if we see HOAC, what we're referencing is acetic acid. So it's not actually running under base conditions, it's running under acid conditions. Right? Since we're running under acid conditions, our mechanism changes. Right? How is it going to change? What's the first step going to be?
Look for, we got electrons on that oxygen.
Ooh. So our first step is to neutralize the acid. So our electrons can come out, pick up that hydrogen. And we form our positive oxygen. Does oxygen want to be positive? No. So what does it do? It can steal the electrons, which is ultimately just a fancy way of doing resonance. Then that resonance is going to place a positive charge on that carbon. How can we stabilize that positive carbon? What charge is the chlorine? Okay, so I heard a lot of negatives, but then I think I heard Lorraine say something else that I liked better. I'm hoping. What's that? Okay, so better, but not quite all the way that I wanted. What I thought you said was chlorine's an electrophile, which means Cl2 is what charge? It's positive. There is no negative. The only way it becomes negative is after a chloride leaves. It hasn't left yet, which means the chemistry of that chlorine, or Br2 or I2, is positive. Why is that problematic? What did we just say we formed in the carbon structure? A positive, which means those are not reacting with each other. All right, so we're going to pause for a second here. What if we ran under base conditions? What happens? Takes the hydrogen from where? Okay, from an alpha position. There's technically 2 alpha. We won't stress about the details on this one. Okay, and we would put those electrons, I actually drew it going to the best space. Let's make it go to the useful space. And we would form, can I form a negative carbon? No, negative carbons are bad, which means this reaction is bad, except I have resonance. What kind of a process am I talking about within this chemical reaction, or what chemistry am I leveraging? This is not the chemistry acid-base nucleophile electrophile. This is leveraging enolates. So this is leveraging the keto-enol tautomerization. When does the keto-enol tautomerization happen? Which is an odd question, but it's a very important one. Say again. Always. The keto-enol tautomerization is always happening. Anytime you have a carbonyl with alpha hydrogens, you are converting to the enol or the enolate, period. It's happening. How much it is happening becomes the question of your individual reactions. Okay? This is why when we look at the aldol reaction, that was discovered because we left aldehydes on our shelves, and it naturally on its own goes to the keto-enol tautomerization. That tautomerization generates a negative carbon that is now nucleophilic that can attack another aldehyde. It's happening to our aldehydes. This is why aldehydes have short shelf lives, because if we aren't paying attention to them, they will all do the aldol condensation reaction and we don't have aldehyde anymore. Okay, so it is always happening. How can we speed that process up? Okay, heat's a possibility. How else? You could add an acid. You could add a base. Adding an acid and adding a base are known as what?
Catalyst.
They are catalysts, which means under base conditions, I get my enolate. And it can chemically react under base conditions. I'm under acidic conditions. What's going to happen? I'm going to get the enol, not the enolate, because the enolate was under base conditions. I'm going to get the enol. How do I get the enol? I still have alpha hydrogens. Those alpha hydrogens are still acidic. I can still have a weak base. It has to be weak now because I'm in acidic conditions. So a weak base can come in, remove the hydrogen, and now take me to the enol. The enol is resonance stabilized, or not necessarily resonance stabilized. Yes, resonantly stabilized. Where I get that active nucleophile again. What can that active nucleophile do? It can now react with the chlorine and we get our substitution. Okay. We're going to enter a little bit of a dilemma here. So before, go for it. I'm going to erase all that now, because mostly I'm going to try and push you to get to the answer a little bit faster here. Let's put the chlorine on. Ta-da. Okay, if we went under base conditions, we put the chlorine on. What happened under base conditions? Say again?
You're talking about like the age rate?
Yeah. Under base conditions, what happens? I still have alpha hydrogens and continues the reactions. What happens under acidic conditions? What's the first step? What was the reactive thing in solution? The acid, which means the first step is we protonate. Is that base, is that oxygen as basic as our starting material? Okay? Because when we did it under base conditions, we said, is that alpha hydrogen as acidic as our starting material? And our conclusion under basic conditions is that blue hydrogen was more acidic because of induction. Under acidic conditions, the first thing that has to happen is the oxygen must act as a base. Is my oxygen more basic in my product than it is in the starting material? How would we decide? What does the base need to do? It needs to donate the electrons to something else. So let's evaluate those two oxygens. They're both neutral, so no difference. It's an oxygen in both cases, so they have the same size. They have the same electronegativity. They're going to have the same resonance. Is there an inductive difference? Yeah, that chlorine is connected. What is that chlorine inductively doing? Taking electrons, which means what happens to the electrons on the oxygen? They're drawn into the structure, making it less basic, which means?
We're done.
Good answer, it stops. Under acidic conditions, you get one substitution. It stops. Okay? Which means we can now go to our answer choices and say, we're under acidic conditions now. This reaction does not continue forward. Which of my reactions sets me up with one substitution? A. Why did it do the internal versus the external? Good question. We're past time. Remember that question next time. I don't have an answer for it. Sorry. Okay. Why are all the other answer choices there? Because you're used to that base condition because of those extra base reactions. Pay attention to your catalyst because your catalyst changes the dynamics of the reaction.